their respective desires.
So what's your name?
What's your name?
Oh, my name is Liao.
Yeah, okay.
Yeah.
Go on.
And to fulfill their respective desires, these lidars must combat monsters in the mirror world and other lidars. And one of the most interesting settings is that every lidar forms contracts with their respective monsters in the beginning. Like this common lidar, Oja, he has 3 contract monsters. Yeah, this one. Okay, this is my scene. This is about Kamen Rider Guy's final window. In the scene, Guy stands on stands perpendicularly on his contract monster, then accelerate to Mach Kong.
Please explain the program.
I want to discuss about the capability of this final event.
What is the problem of the scene? I was asking this to the previous group, everyone, right?
Because he cannot just stand on his monster like the scene.
I don't understand it at all. You need to explain the program first.
Just analyze the possibility.
No, you have to explain the program before analyzing. I was telling this to everyone in the previous group, right? And you are there, right? You're listening to that, right? So please explain the program. What is the program?
Explain what's wrong in the movie.
I said just he can't just stand perpendicularly on his monster. Yeah. This lidar cannot. His vital window is not. It's impossible to do that.
Okay. This is last chance. Last chance. Okay. You are play movie one more time. Explain the program. Okay. This is your last chance. Go. Program in your report. Okay. I don't understand your program, so please explain the program in your report, okay?
Okay.
Next question, please.
Hi, my name is Henry. I'm introduction to the Veruda's final window.
Explain the program while you
Okay. In this season, he used his monster to hem him up and swing to his enemy knight, and then
movie again. Explain.
he used his final window, and then his monster hanging up to the high place, and then swing to the knight, and hit him in the ground.
Okay.
So
What's wrong?
the trajectory is weird. After he released by his monster, he should fly out in a tangent direction. Not like this, and then drop in a vertical line. This is not correct. So we need to simplify.
Wait, but if he's connected to the line, he's gonna go up to the straight, right?
He released at this moment, and then he.
Can you show that again? You need to explain that in a movie.
Okay. He hit the knight, and then we can see here he released. So he do this weird thing without his monster's tongues. And
Okay,
then
I need to see him falling down.
it look like this.
In the movie. I don't see anything wrong in the movie.
he swing to the enemy, and then
Don't stop there. I need to see the whole thing.
after release
I don't think anything's wrong. He just released and it went down there, right? Your drawing is incorrect. Because this scene is taken with a real person acting. So it should follow the physics law.
oh
I don't see anything is wrong. Okay, go to your drawings, that's wrong. Okay.
I take the every frame where he is and place this on this photo, and then every frame he.
No, this is wrong. I mean, this is very different from your previous one, right? He didn't go back like this.
This is every time he in the frame, and I take every screenshot and then contact them together.
No, your red line is different from previous one, right? This guy falls down on the right side.
This red line is.
He didn't go all the way to the top.
Yeah. Without the tongue, he do this trajectory. So this is wrong. He released by a monster at this point, and in the movie, he do this.
He went down there at the release point. He didn't come back to the starting point. Okay, so you need to fix that in the report, but maybe we can see what you did.
Okay. So we simplify this case. Randall
Okay, next.
Okay. This is the real momentum.
he went down there, right?
Yeah.
I mean, this is what happens. Okay, your trajectory is good. This is what happened in the movie, right?
No. In the movie, he is
No, please watch it more carefully.
in the movie he's swing like this. In the red line.
Yeah, and then went down to the rightmost part. So your red line is incorrect. Okay, so please correct that in the report. Okay.
This red line is physics in the seasons, not correct physics.
Not even happened in the movie. You should watch the movie more carefully. Okay?
Yeah, yes. This is what happened in the movie. Oh, okay.
Please make sure to reach that in the report.
Okay, my name is Charlie, and my student ID is 111021224, and my skin is Kamen Rider famous Sword Vent and Strike Vendor.
Please explain my button.
FEMA call her contract beast and beat the enemy. The contract beast called Blockwing. Blockwing blow away the enemy and FEMA kill the enemy. And in the skin, the rider is just stand still and didn't be affected by the strong wind and the high-speed enemy. So I what?
Show it again. Where's the problem?
Oh, in the skin, the rider is just scared, stand still and didn't be affected by the strong wind and the high-speed enemy. And she didn't be affected by the reaction force of her sword vendor.
But then there's no wind at rider, right? So that's fine, right?
But the wind can blow up the enemy, so the wind is very strong, right?
When enemy was blown, but not at the rider's location.
And even the wind is very strong, the enemy are at a high speed too. So why the rider can still kill them and didn't be affected by the reaction force? So I want to discuss.
Okay, wind is already weak at the rider's position, so there's no problem. Okay?
Okay.
So then, is there any other problem?
So I want to. Okay. So I assume the enemy's weight are 70 kilograms and the wind area are 0.5 meters square. So I calculate that. And the wind speed is close to a level 12 hurricane. And then we can calculate the momentum change is up to 3,300 kilograms.
How do you get this enemy velocity? The enemy, how do you get it?
What? Can you say again?
The enemy, how do you get it?
The enemy. Oh. I assume that the enemy's weight are 70 kilograms and the wind area are 0.5 square meter, and I use use the wing pressure formula to calculate the wing speed. It's about 47.35 meter per second.
So how did you get F?
What?
F.
S. Second. What? Per?
F.
Oh, A.
So what's
So-
the number of F? I mean, how do you get
Oh, F is a Newton of wing pressure, and F is the F is the enemy's weight. In order to blow up the enemy, the wing pressure should be larger than the enemy's weight. So I assume that the wing pressure should be 70 kilograms. Is equal to 686 Newton.
Huh? Weight is not a force, it's a different unit.
What?
Weight is mass, right? It's not force, it's a different physical quantity. You cannot just use the weight as a force.
Yes. I didn't notice that point.
So please correct in your report, okay?
Okay.
Weight is not force.
Okay. So after calculated momentum, and since the momentum was equal to the force that female swing her sword, and so the force of the sword against the enemy should be like on the
Sorry, you need to,
Yeah.
so these all numbers are wrong, right? Because if your F is wrong, you know?
yes.
Force, you remember F equals ma? Force equals mass times acceleration. So you need to put in acceleration there in the equation. Otherwise,
Yes.
this is incorrect.
Yes.
So let's go to the next. Did you calculate anything else?
No.
Okay, so what's the conclusion?
What?
Conclusion.
Conclusion. Oh, I think the Kamen Rider female should also be affected by
Is this your
the.
last slide? Go to your last slide, please.
Last slide. So,
That's my conclusion.
Okay, so please correct the number in your report, okay?
就叫你去更正这个数字。
Oh, okay.
So what was your name again?
Okay.
Okay.
What is your
Okay. Oh, my name is Charlie.
say it.
My name is Charlie.
Okay. Thank you, Jerry.
Hello? Okay, where's my okay, so my name is Chen, and this is my ID number, and this is the thing I'm going to introduce. But how can I select that?
What's the name? What is your name?
Chen.
Did you change your name from last night?
No, I don't. I will not have an English name.
I don't have you in my list.
Wait, can I select the link? I found it hard to do it.
I cannot find your name in my list.
Hold on. 哎，这可以选吗？
You forgot your name? Okay, let's go to someone who is in the list first. You later. Please
Okay,
remember your name.
okay.
Let's go to someone else first. Next person, please. Next person.
I know.
Last time,
Remember your name, okay?
last
And tell me.
time you chose another English name, right?
Yes.
Remember your name.
Yes, but yeah. 他先吧。
Oh, okay. Hello, my name is Nick, and my student ID is on the page. And
Okay.
Okay.
You're on my desk. Good.
and for my part, I wanna discuss one of the character called Zoda. He has a crazy skill. Let me show the video. Here you can see that after he fired his gun, then he's sliding backward for a really far distance. Then I think it looks like too far. The distance, the sliding distance is too far. So I'm wondering that if we following the real physics, then what's the sliding distance? Yeah.
Good. You explain the problem. Good.
Yeah, thank you. Then for the data, we assume that Zoda is using a kind of rocket launcher. It's called RPG-7. It's a real gun, real weapon. Then for the data, first the mass of Zoda is 110 kilograms. Then the mass of RPG-7 is 7 kilograms. Then the other data is on the page. Then you can notice that the friction coefficient, I set it to the 0.6 because in a scene, the ground of the scene is looks like made of concrete. So I set the mu equals to 0.6. It's the average friction coefficient of concrete. Yeah.
Okay.
Then first, I want to apply the law of conservation of momentum. Then here's the formula, and after some simple calculation, we get if Zoda fire his gun, then he will have an initial speed of about 5.13. Then the next one, we need to consider the friction of the ground. So we apply the formula of friction. Then the same after the calculation, we get a value of the force. The force of friction is about 997 newtons. Then next we apply Newton's second law of motion, and after calculation we get acceleration is about 5.88. Then notice that the direction of this acceleration is upside to the initial velocity. Yeah.
Right.
Then finally we can calculate the sliding distance. Then here I apply a formula of motion of constant acceleration. Then here's the formula, and also after the calculation, we get the final sliding distance would be 2.24 meters. Hence, it means that if Zoda, he fires his gun, and then he would slide backward about 2.24. Yeah, then here's the conclusion. It's theoretically possible to slide backward 2.24 meters after he fired. But note that in order to simplify the problem, we are assuming that Zoda's body is a kind of rigid object. But I think in reality, there is a lot of factors, another factors like the posture of Zoda and the reflex action after he fired would also affect the final result. And also the recoil of the gun would not entirely exert on the shooter, on the Zodas. So
where does it go?
It would be go spread all the direction. I don't know actually. Yeah, but
Okay. This is good. This is good. Your report your presentation is good. But then in this last part, but in reality, please put a number in here. So what's the realistic number if you don't think it's 2.24? That's
because I think it's too hard for calculation, so I just skip the part. Okay. I will edit.
Your homework.
Okay.
Number, okay.
Thank you. Okay.
But then your presentation today was very good.
Okay. Thank you.
I like your presentation.
Okay. Next
Good.
person.
他先说。
Let's go to Peter.
My name is Peter.
Okay.
迅速召唤武器龙军刀，不要面对更。
Can you explain the program when we are watching? Can you explain the program while watching?
From the image, the Yuki jumped at least 3.4 meters. In reality, even training athlete can only achieve a vertical jump height of around 60 to 70 centimeters, with the world record being approximately 1.6 meters. This far surpasses the limitation of gravity on the human body. And the calculation part, assume Yuki is a professional athlete. He weighs 70 kilograms, and his leg muscles can generate a force 8 times his body weight during the jump. So we can get a force is 5,488 Newton. And the net force have to minus his weight. So we get a net force is 4,802 Newton. And then using Newton's second law, we can get a acceleration is 68.57 meters per second square. And it is known from the video that its charging time is approximately is 0.125 seconds. And we can get a initial velocity is 8.57 meter per second. And due to the conservation of energy, the lowest point will be equal to the highest point. So we can get Yuki jump height is 3.75 meters. And conclusion, the calculated answer is 3.75 meters, which suggests that Yuki could potentially reach the swirl, making it appear physically feasible. However, in the video, he doesn't seem to exert much effort in preparing for the jump, and the swirl may be located beyond 3.75 meters. Additionally, other factors such as air resistance could affect the maximum height. Therefore, it is unlikely that Yuki would be able to reach the swirl. And
No, Peter.
yes,
So your calculation showed that it's possible, right?
yes.
But if you change the conclusion, ignoring your calculation, that's not good. Your calculation, why did you do the calculation? To check this, right? And your calculation showed it's possible, right? And you completely change the conclusion. You just ignore your own calculation, right? That's not good, that's not physics. Okay? We do physics so that the numbers and equations can show the truth. If you get the truth and it completely change at the end because of your belief, that's not physics. This is not very good. Okay, having said, well, that was a little bit similar to Nick. So if you're gonna say that's not possible, you need to show that in number. Okay? But okay, having said that, at the beginning, you said that even world record holder cannot do this, right? And why your calculation shows that's possible? That means your calculation is wrong. So in your report, please find out which part was wrong. I know which part, but I don't say that. So please find it out, okay? And then correct it in the report. That's your homework. Okay?
Yes.
Okay. Jeff,
Okay, I'm coming back. I'm coming back.
what's your name?
Okay, you can call me Starstream another time, but only in this class.
What is your name?
Yeah. Real name or hold on.
Your name.
Real name. Okay. Hold on.
Tell me your name. Last time you told me.
Yeah.
You like me?
Yeah. I just revised it. Okay. Starstream.
What is your name?
Okay, you
This
can.
is your last chance. Tell me your name.
Okay,
I will
you
share this one.
can call me Starstream now.
If you told
Like
me
the last time, huh? So
you don't remember your name. You told me not. Last time you told me your name, right?
yeah, Chen-En. Yeah, Chen-En. Yeah, that's my real name. Yeah.
Okay, I don't have you in my class. Okay, finish. Remember your name, okay? I don't like being lied. If you tell me your real name, you need to remember that, okay?
So I just leave now.
If you leave, you fail.
Tell him again. Your name is Starscream.
So I have to delete that.
No. Tell him again because Star.
I'm Starscream. Yeah, that's my
Okay.
ID. Okay. So
Please remember your name. I don't like being lied.
okay. What is it again? How to paste? How to select it?
You only have 3 minutes.
Okay, so this is Auden. And he is gonna shift. He can shift directly. Like shift one position to another. Like this. He can shift the position from one to another. But I didn't observe any any unreasonable part yet. So I'm going to model the real thing for this part. Like he can shift one part from one place to another, and I model it as he moves, as his moving at high speed like this, which is larger to the 0.1 c. C is the speed of light. Okay, and this is the physics here. The time dilated is equal to the proper time times the gamma factor, and this is the gamma factor look like. How the gamma factor look like, which is called Lorentz factor. Okay. The proper time is the time interval between any two events that occur at the same place. So we must be at the same place in one inertial frame. Inertial frame means the frame that is not accelerating, and is measured by a clock in that inertial frame, and the clock must be close to these events. For example, if I throw a pen to the sky, then the pen is moving, meaning that the event of moving pen is closer to the pen, so the pen will hold the proper time. And I will see the dilated time. Okay, this is the real example for Auden, and if the distance between the moon is like this, I Googled it, and we modeled the Auden moving at high speed will be v is equal to 0.9 c towards the moon. And if we can move towards the moon, then the observer on Earth will see Auden teleport to the moon. So we can know that. So Auden will hold the proper time because he's moving, and the one on Earth, the observer on Earth, will see the dilated time. And then we can calculate the proper time because he's moving at the same speed. Okay, so then we derive the Lorentz factor. Then we time the proper time and Lorentz factor together. We'll see the dilated time, which is much, much larger than the proper time. This is my conclusion. Once an object is moving at velocity over 0.1 c, we'll need to use the dilation formula or the relativistic moment and relativistic how is it 运动 in English? Okay, we need to use that formula to fix it when an observer measures the time it moves. Because if you take the limit at the Lorentz factor, where is it anyway? Okay. If you take the limit that v is approaching to 0, the gamma factor will be 1, meaning that if your velocity is closer to 0, then the time dilated is nearly the same as the proper time. And if the traveling distance is getting larger, the dilation effect will be much more significant. And this is my reference. Okay, thanks for listening.
So what is your problem?
I explained it.
Okay, I didn't understand.
Oh, like, hey, where is it?
You failed to explain. So you don't see any problem in your movie, right?
Yeah, he's moving at high speed, like, eh?
And your time direction concept is you're misunderstanding it.
What, really?
Yeah, I mean we don't see anything faster because it's faster. I mean we just see the speed. It's just the difference is the clock. It's just the time is relative. You're misunderstanding this concept. That's wrong.
Okay.
And although this report is about finding a problem in a movie, right? And explain it, right? So did you do that?
I didn't. I didn't.
Okay, so please do that in your report, okay?
Okay. Okay. Hello? Can you hear my voice, Professor? Hello? Professor?
internet connection problem. Maybe his internet connection is not good. He just left the meeting.
Okay.
Yeah, but I'm not sure.
Please tell the professor about this.